All right, let's take a look at some of these for a review. So, I'm gonna start with 19C, and then we're gonna do maybe a couple where we had to convert to a Fisher projection. Okay, and then we'll take a look at some of 9, 13, 22 as well. We'll just see how much we're able to get done. So, because a lot of them, of course, the process is similar, right? So, once you can do one stably, for the most part, you can do most of them. Okay, so 19C, we have... Alright. This is our given molecule. Wow, that was actually a pretty good chair. Okay, we've got a chlorine here and an iodine here. I have no space, as always. But, perfect. So we've got our things there. We're looking at the IUPAC name. First thing we want to do is determine R and S. Remember, for cyclohexanes, we're kind of looking at... is already kind of in 3D. So if we're looking at the iodine, we're looking at these three as our non-H's, right? And so we kind of want to look at it from that angle. We can see the iodine's coming up towards us, kind of. Or rather, the iodine and the left carbon are in the plane, and that front carbon is coming towards us. That's kind of our wedge, if I want to think about it that way. And this is kind of our dash here. Somewhat. So if we want to consider instead the hydrogen R dash, that would work too. We're just looking at it kind of right over here. We see the iodine going up, the carbon to the right, going towards the chlorine is number 2, and the other one is number 3. So 1, 2, 3. This is an R stereocenter. And if we want to look at this one, we're kind of looking at it from below, such that our chlorine would be like kind of up top. You'd have, like this way, we're looking from below, so chlorine is kind of not where it seems. Chlorine, like, if we're looking from below, chlorine would be straight up, right? So we're looking at 1, 2, 3 in an R fashion as well. And so this one should be RR. And I hope that's what I have on the key, or else I'm just gone crazy. So I believe this is RR then. With that, we're going to name this 1R, 3R, 1 chloro, 3 iodo cyclohexane. And if we're looking at drawing this as a double Newman projection, we just kind of want to choose how we want to look along those. I think it's probably a good idea to look along the 2 bonds that have our halogens on them, which would be these 2. If you look along those 2, remember when you're doing double Newman, it's a parallel thing you're looking at. So our front carbon for the chlorine side has chlorine here. It's got the other part of the cyclohexane, it's got hydrogen up. Our carbon with the iodine has iodine up, and it has a hydrogen to the right, and we have the back of the cyclohexane as well. And then on the other stuff, we've just got hydrogens everywhere, right? Nothing special there. Remember, you just kind of want to isolate a pair of parallel bonds to look at for double Newman. And so it would make sense to do the ones with the chlorine and the iodine, right, as the front carbons. We could do them as the back carbons, but that's just more work. All right, and then this question, we want to do a diastereomer, so we can switch a chlorine and a hydrogen or an iodine and a hydrogen. Doesn't quite matter. Either one would work. We could say, aha, I've moved now the chlorine up here, hydrogen here. As long as we don't change both of them, it'll be a diastereomer. We could have switched to the iodine with the hydrogen on that carbon as well. That would work too. So we're good. Either way, this will work. So that's how we would come up with the projection there. Alrighty, so how about we do the next one, since that's going to be one that has a Fisher projection for us. If we have a sawhorse, we have a sawhorse already. Sawhorse makes it, that's kind of our best bet to get to Fisher correctly. My understanding of actually your question is just converting them to Fisher. So I'm going to skip the stereochemistry in the interest of time, if that's okay. But if you really want, just check the key, I suppose. You'll see what the answers are and see if your priorities are not quite correct on it or something. So if we're putting this in Fisher, it says here we want our propyl on top. Let's not worry about the enantiomer yet. Let's convert this thing into Fisher, and then we can switch to the enantiomer in a second afterwards. So okay, so if we're going to do this, let's go ahead and we probably want to rotate it so the propyl's pointing down. Remember that if we want something pointing up in Fisher, that means that we need it pointing down in Sawhorse. So if we redraw our back carbon pointing down, let's rotate everything. I'm going to move this just a little bit back. If we rotate everything 120 degrees, what is this, counterclockwise, our propyl moves down. Actually, this will be 60 degrees. Our bromine will move up to the right, and then our hydrogen will move to the left. And so now that we have our propyl pointing down, that's the one that we want. We're just going to leave the front carbon alone. That doesn't matter. And so this tells us that we've got propyl here, we've got butyl here. Remember, Fisher, everything needs to be pointing down. And now we see everything that's on the right and on the left. So we've got bromine and hydrogen, and then we've got hydrogen and bromine. So this is the kind of original. The enantiomer of this, which is what we're asked, would just switch everything that's horizontal. Keep the top groups the same. Switch all the horizontal groups. This is our enantiomer. All right, and if you want to do these for purposes of stereochemistry, if we look at this carbon here, first priority is bromine. Second priority would be the top part of that molecule. Third priority is butyl, so we have to switch the hydrogen. The hydrogen and the butyl have to be switched, or the second one and the hydrogen have to be switched, and then we'll do a switch. So I'm going to switch this top part with the hydrogen. Oops. So 1, 2, 3, and then so that gives me R. But since we switched stuff, this is an S. And if we do the same thing here, we're going to see bromine is number 1. Then we have the bottom carbon is number 2. Propyl's number 3, so we're going to have this one will also be an S, because we would need to switch our hydrogen with the propyl, and so we're going to get R normally, and then we're going to switch it to be S. So then, presumably, if I've done that correctly, which I hope I have, these would both be R's. All right. Cool. Let's do the one before this. Let's do part B. Let's do 19B, so we can see the arrangement here. So we have a Newman projection. We're going into Fisher. So we have methyl, propyl, hydrogen. Again, I'm going to just omit the stereochemistry right now. Just check the key. And if there's still questions, then we'll go over it next week or something. Since I know the key was only posted a couple hours ago. So, If we want this as a Fischer position with ethyl on top, we want to rotate this Newman so that ethyl is pointing down. Leave your front carbon alone. We're going to move this, I suppose, 60 degrees clockwise. So we're going to have H up here, and then we're going to have bromine up here. As this is drawn, we have methyl and ethyl here. Hydrogen and bromine on the right. Propyl and hydrogen on the left. And then we want the diastereomer, so we just got to switch one of these. So we could switch these two. Or we could switch the propyl and the hydrogen. Just swap any two things on the same carbon, and that's all we need to do. So this will be a diastereomer. Diastereomer. Okay. So what you want to do for all these to go to Fischer is arrange your Newman or sawhorse as eclipsed with things pointing down. That's how we go to Fischer, remember? So everything has to be pointing down. And so that's why we need those there. And then everything else, this is going to be the wedge or the right side. This will be the dash or the left side of our Fischer projection. So these are going to be the top and bottom. In this case, I mean, I've written out which we're putting on top, so we put the ethyl on top. That's still a pointing down position, right? So Fischer is special, and that's the way that things are done for that. All right, so cool. If we look at number 9, we're just looking at any carbon that has 4 different things on it. Any sp3 carbon. I would just check the key on that. Ask questions if they come up. This is pretty straightforward. So just look for anything that has, if it's an sp3 carbon that has 4 things, that's good. Or if you're on a double bond, where you have a non-ring double bond, that is, that you could potentially have cis-trans or E and Z stereoisomers. So if one side of your double bond is different than the other thing on the same carbon, then you could have stereocenters there. Okay, so just keep that in mind. All right, and then number 13. Draw them using the mirror image method. Okay, so these are fairly straightforward as well. Let's do some more complicated one. How about we do the second one? So the second one looks like this. Some nice bicyclics going on. If you want to draw an enantiomer using a mirror image, that's you're just drawing the opposite of what you see. So draw it as if it's in the mirror. So everything that's pointing like to the right becomes pointing to the left. And therefore this would be your enantiomer for this. So that's all it is you just reflect it. You draw the mirror image of it. So like of the number 3, the mirror image would be kind of an epsilon. So that's what you're looking at. You're just looking at things that are pointed. Things will just kind of change which way they're pointing. So up and down stays the same, but left and right switches. All right, and then 19, we did some of that. 22, let's do some of that. Let me scroll down. Where's 22? Oh, okay, so draw all the stereoisomers of 2,3-dibutane. So that'll just be whatever combination of wedges and dashes you want. So we have these. Those would be the 4 different ways of doing this. You have 2 stereocenters on this, so you're going to expect 4 stereoisomers, right? 2 of these are meso, because if we just kind of do some symmetry, if we rotate our molecules, we're going to see that we end up with the same thing. And that would be these 2 over here. These are the meso bits. So because these 2 are the same, if we were to just rotate this if we were to stick a line straight through and rotate 180 degrees, if we do that, if we stick it and then rotate 180 degrees, we get the same molecule as the one on the left. So if you rotate it around that dot 180 degrees, whichever direction, counterclockwise or clockwise, doesn't matter, you'll end up with your bromine on the wedge on what apparently is carbon 2, and then the bromine on the dash for carbon 3. So that's the meso one. So normally these are just their own stereoisomers. So A and B are the same compound. They are meso. And so remember, we're looking at symmetrical things, how we can possibly get these 2 to be the same. That's our symmetry there. So we're looking at that, and we get that as meso. So normally you have 2 to the n stereoisomers, where n is your number of stereocenters. Now, stereoisomers. So 2 to the 2 is 4. Having a meso one means that you have less than 1 than you'd expect. For every meso, you end up subtracting 1 from your total. And then if we want to redraw, because again, I've done these as non-Fisher projections, but if we did them as Fisher projections, our meso ones are a little bit easier to see, perhaps. That would be these 2. These 2 are the same. Oops. And we have, let's see, what else do we have? And then we have the other side, our other isomers. So if we were to redraw these as sawhorses, I'm going to just draw one of them as a sawhorse, and then we'll rotate it, but the process is the same. So sawhorse, that tells us the methyl groups are pointing down. So in the back, we also have, I'm going to just make this a little smaller. We have our methyl groups pointing down. In this case, we have the bromines on the right side of the molecule, hydrogens on the left. So this would be our sawhorse. If we want to stagger it, we just need to rotate it so that our bulkiest groups, in this case the methyls, are opposite of each other. You can rotate either one. I'll rotate the front because I feel like it. If I do that, if I'm rotating that one 180 degrees, bromine is here, hydrogen is there, and our back one stays the same. I could have rotated the back one instead. Either way, you'll end up with the staggered sawhorse this way. So we've got our methyl groups anti to each other. And so that's how we would do that. And so it would be the same for all these. So I would redraw them originally and then rotate afterwards. All right, so that is 22. And yeah, so I think the biggest problem here is converting between Fisher and Newman and Sawhorse and Wedge Dash. As always, this is something that takes practice. So make sure you spend some time with the key. Make sure you really kind of dig in and see exactly what looks weird, what's been difficult, see if you're getting the right answer, see if there's a pattern that things are getting wrong. So maybe like every time you try and do RNS from a Fisher, you're getting it wrong, then next week we can be prepared to talk about that. specifically doing RNS for fissures, because those ones I don't normally include my work on because I just find it easier to do it in my head. But if you're having trouble with a certain projection doing RNS, I'm happy to then take some time next week. We'll do another review and we can go over that. So again, sorry my internet's being wanky, so I'm gonna have to record this like kind of specially, but yeah, I don't know. I have to figure out what to do with the 101 students, so we'll go from there. Alrighty, well, if other ones come up, we'll do them next week, and we'll have those. So, alrighty. If there's more, I might have time later, but I just don't know yet. So, we'll see. Internet's been bad like the last couple of days. I don't know why. So, hopefully it'll be fixed by next week. Alright, there we have it.